Welcome back to the discussion of spatial data mining. In the last few videos, we first tried to define what spatial data mining is and what it is not. We gave examples of several pattern families, and then we also went and looked at the input, spatial data types, as well as spatial statistical foundation. So some of you probably recall from last video that spatial data often violates common assumptions made in statistics, such as data samples are drawn independently of each other. Right? Spatial data, when the first law of geography says that nearby things are similar. So in other words, spatial data samples are often not independent of each other. And this is often quantified as spatial autocorrelation. And you saw at least one way to quantify that in last video. Okay? In this video, we are going to look at the impact of spatial autocorrelation on one pattern family, namely the location prediction. Okay? So at the end of this particular video, we want to very clearly distinguish the classical prediction problem and location prediction problem. And second, we want to see how this autocorrelation impacts basic prediction models such as regression. Okay. All right, so without further ado, let's recall the location prediction problem. So you remember in the very first video in spatial data mining, we brought up this problem of predicting locations where a bird likes to nest. Okay. The other location prediction problems relate to things like spread of infectious disease or landfall for hurricane or tornado and things of that kind. Okay. But in the bird nest problem, we are essentially looking at a map. This is a wetland near Lake Erie. The green areas are vegetation, white areas are water, and then you see little crosses around the edge and so on. These have been the old nest locations. So a graduate student very painstakingly went to this wetland and mapped out the entire area into 5 meter by 5 meter grid cells. Okay? And the grid cells with nests were marked with X. Okay? So given this data, we want to predict that in future years where these birds may like to nest. Okay. In addition to bird nest, we also had many explanatory variables. So here is vegetation index. So these birds often prefer dense vegetation because those do not sway too much with the wind. There is water depth, and then there is distance to water. Again, distance to water is a proxy for protection from predation. If the nests are really at close to the edge, then dogs, cats, and other kind of predators can attack. Okay? So there are several such other maps, and given these explanatory variable maps, we want to build a model which can assess the nest worthiness of various sites. Okay? So this problem actually may remind you of many classical prediction problems. If you have taken any course in machine learning, statistics, or even data mining, then you can pose this problem in terms of their models. So for example, if you imagine a tabular representation of this data, where each pixel is thought of as a row in the table, and there will be 4 columns. So there is a nest column in that table which may say yes or no, and the other 3 columns, vegetation index, distance to open water, and water depth, may give you numerical value. So given such a table, you may ask what prediction models you will use. And this place you may want to pause the video and think about those. When we come back, very likely the first model that will come to mind is this regression model. Okay? This is the most popular prediction model. In fact, areas like marketing, people have said if you know your problem well, all you need is regression. In other words, if you can select very good features, then this simple model will work. Okay? Others may use Bayesian classifiers or neural networks or SVM and decision trees and so on. Okay? The arguments we will make in context of regression will apply to many of these other models. But to keep the discussion simple, let's look at regression. And remember from statistical foundations, regression assumes that data samples are drawn independently of each other. So what happens when you apply it to spatial data, where we do know first law of geography tells us that IID is not true. Okay? But if you go ahead and apply this model, y could be the nest and x could be all these prediction variable, and if you run it through a software, it will learn some coefficient beta, and it will try to give you some model. Okay? But what's the implication of violating the IID assumption behind regression? Okay? So if you went through this, essentially the following things will happen. These models in linear regression may give you a weaker model. It may have lower prediction accuracy and so on. Okay. So in contrast, people have introduced this new model called spatial autoregression, where in addition to this linear combination of explanatory variables, there is a new term rho WY. Okay. So let's briefly understand what this term means, and then we'll go into a case study. So this W is a neighborhood matrix. Essentially, given 2 pixels, it tells us whether they are neighbors of each other. Are they close to each other or not? And then rho is a scalar. Rho is just a number. It tells you autocorrelation. Okay. So data sets where nearby locations are very similar, rho will be close to 1. If nearby locations are independent of each other, like the white noise, rho will be 0. Okay. Conceptually, there can be a negative rho. So if these birds don't like each other, they are very territorial, and they push each other away, then you could have a negative rho. Okay. So in this spatial autoregression model, we will learn this rho and beta. Okay. The traditional way, we actually give W as an input. We tell which locations are neighbor of each other, and it's usually based on distance. Okay. So let me actually go back to previous slide and quickly show you what W looks like, and then we'll come back here. Okay. So suppose you have a very simple map with 4 polygons A, B, C, and D. So in this case, the neighbor is being defined by adjacency. So you may come up with the neighborhood matrix like this W, which is shown in the middle. And for example, polygon A and B are adjacent to each other. So there is a 1 in row for A and column for B. Okay. But if you see the row for A and column for C, there is a 0, means polygons A and C are not adjacent to each other. This is one way to define neighborhood matrix. You could also define it by distance. And once this neighborhood matrix is defined, sometimes people do row normalization. So for example, in case of B, there are 3 neighbors, A, C, and D. So we essentially divide each number by 3 in order to make sure the row sums are constant. Okay. So coming back to this model, essentially spatial autoregression is telling you something different. Okay. In regression, we said that nest at any location is completely determined by the explanatory variables at the same location, the water depth, the vegetation durability, and so on. In contrast to that, spatial autoregression is saying you something different. It's saying that nest at a location Y on the left hand side is only partially determined by explanatory variables at that location. Okay. But it's also determined by nests in the neighborhood. So W is the neighborhood, and YW essentially is telling you nests in the neighborhood. Okay. So again, try to think about what it means, for example, in our own choices of homes. Okay. So if you look at a city, the first dwellers come there and they pick the best land to build on. These are high land protected from flood and all that, right? But then the city grows and more people come in there, and they are coming there because there are jobs, and they may pick sites which are not the best sites for building houses. They may build houses on low land which are prone to flooding. Okay. In fact, some of you, if you remember Hurricane Katrina in New Orleans, you may want to look at the map of flooding there. And what was surprising is the following. French Quarters, a major tourist attraction, was not flooded, but a lot of downtown and other nearby areas were flooded. And again, think back and see why that happened. The first settlers came and they settled in French Quarters, which was a high protected land. And then more people came and, and they just settled near that area. So that's the rho WY term. People are social, birds are social, and partially we go and live where other peoples are, not particularly where the places are the best. Okay. So that's what spatial autoregression says. And in case your data does not show autocorrelation, in case things are independent, when you learn this model, rho will come out to be 0. So you're not losing anything. This model is strictly more general than the previous model. Okay. Autocorrelation can be incorporated in other prediction models. So if you know Bayesian classifier, which looks something like this, where probability of a class at a location in classical Bayesian classifier is dependent only on explanatory variables on the same location, and you can write Bayes rule and try to learn an underlying model. But in contrast to that, we can bring in spatial autocorrelation. In this world, this is also called Markov random field, and you can rewrite this equation and say that the probability of a nest at a location is only partially dependent on explanatory variable at the same location, and it's partially dependent on nests in the neighborhood, and you can build models like this. Okay. So this is the mathematical representation, but let's go and look at a case study. So the bird nest data set that we showed you was part of a PhD thesis in Department of Ecology at University of Minnesota. And initially the PhD student, Yuga Ozumi, he tried linear regression. He also tried neural networks, and his predictions were very poor, only about 50-55%. So this is what he was experiencing, and this is what many have experienced. If you ignore autocorrelation and you continue to use models which make IID assumption, you may have lower prediction accuracy. In addition, your confidence in the model, the R square, will be low. And worse yet, if you make a map of residual errors, those maps will show autocorrelation. So you will see a lot of positive errors in one area, a lot of negative errors in other area, and so on. Okay. So can spatial autoregression models help? So finally, in his thesis, spatial autoregression was tried, and these curves are showing you a little bit of the impact. Okay. So in this one, we are showing you the ROC curve. The dotted line or the dashed line is linear regression, and solid line is spatial autoregression, and you can kind of see 10 to 20% improvement in prediction accuracy, both for learning as well as for testing. This was also tested for a different wetland than the map we showed you. Okay. So many other people have found similar benefits. Okay, but it is computationally more expensive. In order to try this, you need special software. This is implemented in MATLAB, or you can go use packages in R, and you have to have a little bit more CPU horsepower in order to crunch the data sets. But it's worth in many of the spatial data sets. Okay. There are other models. If you remember our statistical foundation, spatial autocorrelation was the first law of geography, but then we went beyond and we looked at other issues such as heterogeneity. So people have also tried to generalize linear regression kind of models to account for spatial heterogeneity. Okay. One such popular model is geographic weighted regression. And what it does is essentially to state that we may have a linear relationship between a prediction variable and explanatory variable, but that relationship may vary from place to place. In other words, the weights for different explanatory variables may change. Okay. So in this case, in GWR, the form of relationship is left alone. You are still using linear relationship. Maybe nest at a location is explained by prediction variables at the same location. However, beta is a function of location. Okay. So beta are location dependent. Okay. So when you learn this regression model, then instead of learning scalar values for beta 0, beta 1, beta 2, all the elements in beta vector, what we are learning are maps. So your the beta naught varies from location to location, and here the intensity of the color is showing that. Beta 1 varies from location to location, beta 2 varies from location to location, and so on. Okay. Of course, in general, you could combine both model. You can combine spatial autoregression and GWR and model both first law of geography as well as second law of geography, and so on. Okay. Again, GWR is widely available. You can just go to Wikipedia, find software packages which implement it, and try that out. Okay. So with this, we'll try to wrap up the discussion of location prediction models. And again, key messages are that spatial autoregression matters. Okay. Many spatial data sets samples are not independent of each other, and modeling spatial autocorrelation in your model often improves prediction accuracy and the goodness of fit. It also reduces autocorrelation in the residual errors. We saw example of spatial autoregression, and we also saw a little bit about geographic weighted regression, which is a way to model heterogeneity. Now this field is still evolving. Okay. A lot of developments have happened in last few decades, and there are still new ideas that people are looking at. So one such idea is, for example, we had in spatial autoregression, the users provided the W matrix, the neighborhood relationship. And with the advent of big data, now as we have more and more data sets, people are getting more ambitious, and they're asking, could we estimate W out of the data? Okay, so this is one new opportunity in the field. Another issue is, if you look at the terms inside spatial autoregression, the two terms rho WY and X beta often tend to have very different magnitude. Okay. Because W is normalized, rho is between 0 and 1, and Y is only one vector, whereas X essentially ends up having very large magnitude. So X beta can often have very large magnitude relative to rho W beta, and this kind of scaling issue often has to be addressed in order for us to get reliable estimates of both. Okay. Let me also mention one other aspect which has not been modeled very well by statistical thought, which has to do with your error measures. Okay. So in space, if you remember our data discussion, we have many interesting operations and functions, one of which is distance. Okay, so let me illustrate how that may play a role in location prediction. So let me first show you a quick example. So suppose here is a continuous map. Somebody went and took a picture of an area, and we found 3 bird nests, which are the 3 dots with circles. Okay. When we discretize this map into a grid, we probably, let's say, have 4 by 4 grids, and 3 cells, the lower left corner, the lower right corner, which are listed by A, and this place were marked as actual nests. Okay. Now consider 2 different prediction models. The C is one prediction model which predicts nests over here in upper left corner with 3 P's, okay, whereas actual nests are down here. And let's look at another model D, which predicts nests sort of in the center with 3 P's, and the A's are still at the bottom. Okay. So again, what I would like you to do is to pause the video at this point and ask yourself, if these 2 prediction models were given to you, which one will you prefer? Okay. And I have often asked this to many audiences, and lot more hands go up for model D. Okay, lot more people prefer that. Okay, and then I also ask you to pause and ask that all the statistical models we learned, whether it was regression or whether it was spatial autoregression or Bayesian classifier, how will they rank model C and D? Okay, so again, pause the video, think about it. How they are ranked, and they are usually ranked by the number of errors. So in this case, there are 16 pixels, and note that statistically you have 6 errors in model C, because all 3 positive, the P predictions are false positives according to statistics, and actuals are true negatives. And the same 6 errors happen in model D. In other words, statistically C and D are the same. Okay, so why do most people prefer D? And again, most of the answers that come back saying that if you look at the actual distance between prediction and actual, those distances are much smaller in the model D. Okay. In other words, statistical ranking does not take into account simple spatial relationships such as distance. It treats each pixel independent of each other when we talk about error. But most of us do have other spatial notions, and they prefer model D. So this is something again which is hard to model in current statistical model, and currently in terms of research and other explanation, people are thinking about it, and they are looking at notions like putting a penalty function in order to favor the distance kind of method. Okay. So let's kind of look back on this video very quickly. We primarily talked about location prediction problem, and we distinguished it from classical prediction by pointing out the presence of spatial autocorrelation. Our learning samples are not independent of each other, and distances between pixel matter, as we just talked about. Because of that, people have introduced new model. So linear regression has been generalized to spatial autoregression by adding this neighborhood term. Even Bayesian classifier, you can bring in Markov random field. And in research, people have done similar things for decision tree. So there is a thesis working on spatial decision tree and so on. Okay. So by at least using the current model with spatial data, you are likely to improve the model accuracy. And as time goes by, there will be new ideas coming. Hopefully, you will also be contributing to some of these ideas. So with this, we'll wrap up the discussion of location prediction. When we come back in the next video, we'll look at one other pattern family. Thank you.